So we got there. All right, so today we're going to change subject, and we did some multiprocessing, multi-threading, and basic features of what basic feature design, basic differences between Python and other languages like meta-classing and basically everything in an object and so on. So we have a good introduction to Python and to its peculiarities. What I wanted to start today and then go on for the next 4 or 5 lectures is actually more of a discussion about design. So how do you structure an application? How do you decide what to create as classes, as how to couple classes together, when to extend the class and create a subclass, or where to actually create other kind of patterns. And the first thing that I wanted to look into is actually what is inheritance in Python, deeper look at that. What tools you have today in Python 3.7, 3.8 for inheritance, so also protocol, abstract-based classes, and then look at how to use those and when to use those. In the future lectures, I wanted then to look at the standard problems that that you might encounter, like standard setups, and look at standard patterns to implement those kind of setups in a nice way. But before we can actually look at standard patterns, we need to take a deep look at inheritance in Python from the ground up. So before we look at inheritance in Python, the first thing you do when you start programming in your application is you have a goal in mind, right? And that's what you want to achieve with your application. And you start dividing these into different things, different tasks that you need to, like, for example, one is communication in networking. The other one is probably generating the content, simulating something, or the other one is learning something in a machine learning setup. And you want to kind of set up these different tasks to achieve your goal. And once you have this mentally, this is even before you start typing one single line of code, you start breaking it down into different steps for each task, right? That you want to have, and how do they depend among each other. So this is where you start. Now you have this this kind of picture in your head of what it should do and how it should do it. Now you try to match it to what you know about the language. This is the process where you start designing your architecture, and it's quite a complex process. I mean, it's taken for granted most of the times, but it's actually, once you start writing programs that are beyond 10,000 lines, 15,000 lines, you start to get a bit involved, and it's not always obvious which choice to take. So the first question that one wants to ask is, what is a good architecture? What is a bad architecture? Before you actually decide which architecture to take, you should actually consider what makes the choice I make good, right? There is I mean, before we go into that, okay, what is an action architecture? So you want to decide which models you are going to write, which dependencies are between these models, and how is the coupling between them? Is there a precise API, or are there basically very tight coupling between 2 or 3 classes that need to be there for reasons that we will see? Also, are you exposing an external API? It's important. It's a choice that you have to take, right? And then also there is a choice. I mean, you don't program in vacuum. So is there an existing framework that you can use? How does this framework influence your architecture? Because if you implement a certain framework, for example, in UI programming, if you implement like well, Python, there's not so many, but for example, if you implement Angular in JavaScript, you would have a very precise design pattern, how you want to proceed with the programming of your views, right? So this is very, very specific. There are other frameworks that are more loose, but again, if you're implementing a framework, this also has a great influence on your architecture. So then again, how do you decide what is a good architecture? And there are, over the years, over the years, there have been a lot of discussion about this. And there are 2 principles that make that everybody agrees upon and make an architecture good. And these one are cohesion and modularity. So what does it mean? Cohesion means that functionally related parts of a code are in the same module, class, method, whatever the basic unit of programming that you're using are, right? Depends on what language you use. So in Python would be module, class, method, meaning that if you are doing networking, right, in your program, that networking piece of code is not spread across all the different modules of your program, and each part does its own networking, but actually there is some piece of code responsible for networking, and if you're debugging or implementing or augmenting your networking code, then you actually have to look into that part, and it's easier to test. Can you please mute yourself? Thank you. So that is the first part. The second part is modularity, meaning that within a certain method, function, or class, there are no two different pieces of code, pieces of unrelated pieces of code, right? So that different parts of your functionality are actually separated and connected only loosely. That's important. It's not enough to separate them if then they're completely interdependent, and whenever you change one, you have to change the other. That is not modularity. This is just separation files. So if you have this kind of features in your code, you end up with something that is readable and maintainable. And this is what you want to achieve. This is, again, why are we doing this? I mean, if you're doing research and you're writing your own code and you're the only one that uses it, you probably are fine anyway. But if you come back to your code in 6 months because you want to follow up on what you did, you're probably going to end up in trouble also if you're just working by yourself. But the moment that you're working with someone else, you want actually your code to be modular, you want your code to be readable, and you want your code also to be cohesive, because you want to share this functionality with someone else, and you don't want the work of your colleague to influence yours directly every time, so that when he commits, your code doesn't work anymore. And at the same time, you don't want to spend hours debugging together code because nobody understands what the other did, right? So these are important things. And what happens if you forget about one of the two? Because it's easy. I mean, if you start spreading your code into modules, then you start, for example, having issues like, okay, I need to save files here, I need to connect to the network, I need to do things, and then you start replicating. You're replicating the pieces of code that are across your whole application. What you end up is something that is repeated, confusing, hard to read, hard to understand, right? Because you don't know that there's different standards. You started doing it working in one module, you did it one way, then you did it in the other module. Maybe it wasn't even you, somebody else did it, and it was done in a different way. Then it's not consistent across it. If you have to debug it, you have to debug it independently. On the other end of the spectrum, if you don't have cohesion, you have interdependencies. And then you start changing A, and suddenly everything else changes, and you're not able to track it, debug it, and so on. So, but it's not rare to have this kind of problems, because again, the code is something that is living, so you have this neat architecture at the beginning of your program where everything fits, and then some requirement comes in because you want to do something else with your code that you didn't foresee, and then you start having a new dependency and a new connection between your classes, and then another part of the dependency comes in, and then you have a new connection. Then somebody else edits your code, it doesn't understand your design, and implements something that actually creates new interdependency, and you end up here. This is a typical drift that goes from here to here, right? And the same way in the other direction. So, but these are the principles that we want to uphold. What tools do we have at our disposal? So the first thing that we have is subtyping. So not subclassing. Before we go into subclassing, we discuss subtyping. Subtyping means basically defining an interface. Well, everybody knows what an interface is, and implementing it in a certain way. Now, subtyping can be explicit or implicit. In Python, this is not always explicit, right? But at the minimum, you want to have basically a method declaration, whether it's explicit or implicit, because you call those methods in other classes, and a method implementation, and that's what subtyping means. So we differentiate between name-based, when you explicitly tell what's a superclass is, for example, in inheritance, and when you overwrite explicitly the methods that you have defined in the interface, or it can be structural, when you, for example, in your code, you call something object.print, for example, and you expect that object to have the print method, but you didn't define it like that, right? So that brings us to the Python specific stuff. So exactly, so at the minimum in Python, for subtyping, you just need to call a method and expect that it's there. So Python does not require us to subclass, right? It does not require to declare the original type, or to declare what type are you using there. Like, for example, if you expect a function to have an array, it doesn't expect, it requires you to declare that that object should be an array. You can just pass it as any, and then you assume it's an array, right? And also, Python will only complain at runtime if something is wrong. Basically, it tells you the attribute is not there, so you did something wrong, right? But while this is very flexible, it's also very dangerous. So today we'll explore a bit of things that you can do to avoid this kind of mistakes. What is the spectrum of typing? So first of all, we need to differentiate between static typing, subtyping, and runtime typing. So if you start with static and nominal, this is a standard inheritance, right? So you can check this at statically, compile time, or at inspection time. If you have an interpreter, you still have an editor that can inspect your code and tell you if something is wrong. But to do this, you have to be able to see those dependencies in code. If you need to first instantiate your system, create the object, pass the object, and then check if that object is actually the right type, then you're not able to do it statically and at that level. Whether it's structural or nominal, it doesn't matter. You still have the problem that you cannot check it statically. So if you do not declare your object, for example, by declaring the superclass, but only implementing the methods like you do in Python, you still can have structural static typing, and that's something that we will discuss today. It means basically that you say, in this function, I expect something that fulfills a certain interface, and then you pass it an object, and the editor, for example, or a tool that checks your code can actually infer if that object has that interface, because it knows the object definition, so it knows which methods it implements, and it can then check it for you. This is done, for example, in many editors and in other tools. Then there is the runtime, right? And then in runtime, of course, if you don't have anything, if you're just doing structural runtime typing, it's what is called duck typing. So we talk about this. And if it's nominal, it's just, if you want to implement nominal type checking at runtime, you just call existence. That's what it is, right? It checks that you actually pass the right distance. So let's explore this in detail. What is duck typing? Well, duck typing is the standard for Python. It means that if it looks like a duck, works like a duck, and walks like a duck, it's probably a duck. Right? So that's the standard. It's very flexible. It's very quick to implement. You don't have to follow any procedure. You don't have any boilerplate code. You just write your methods. You expect them to be there, and it just breaks if they are not there, right? Simple example, what you've seen every time in Python, you define a class with the method next, and then you define another function that expects that class and just call next. You don't know that this object has next at inspection time, I'll say compile time, but there's no compilation again. But you expect it because you know your structure, so you just write it. There is no check, there's only the runtime, right? The other end of the spectrum, you have the standard subclassing procedure that you have been using for basically all your programming life, which is basically to define an interface, right? In this case, it's the old way to define an interface. So by raising not implemented error in the interface. Interface in Python, in standard old-fashioned Python, is just a class where the method raise and not implemented error. That's it. It doesn't have any particular difference between this as an interface. And that this is a lot of disadvantages, of course, because statically, the editor doesn't know the difference between this and a normal object. There's no, I mean, it has to do deep inspection of the code to understand that this is an interface and help you out. But at runtime, it's pretty easy. At runtime, if it calls that method, it will tell you, hey, this is not implemented, right? So, but if you implement it this way, you are actually nominally secure that this object implements this interface, and when you call it and you specify that you require that, you're in fine shape, right? So the editor at the minimum will tell you this object implements my iterable because it follows the object inheritance structure, inheritance tree. So this is all fine. Problems, you only see the errors at runtime, and you have a lot of boilerplate, right? Because you have all the raise exception in the definition of the code. So what are the new options that you have to implement subclassing and subtyping in Python 3? The first one is ABC, abstract-based classes. The idea of abstract-based classes is to implement what in Java are abstract classes, right? And they provide all the tools to do it. The way you do it is by either using meta class ABC meta or by subclassing ABC. That's two equivalent ways. ABC basically, like this, without the meta, is a utility class that just implements meta class ABC meta for you, so you just subclass it. But there's no difference at all. You have also abstract method, you have also abstract property, if you want. I didn't put it here, but basically it implements the abstract condition on properties. And what are the advantages here? First of all, it can be checked statically that is an abstract class. So the editor can help you out and say, okay, watch out, you're instantiating something that is abstract, so you shouldn't be able to do it. And also it protects you from instantiating at runtime. So while in the previous example, I could have just instantiated my iterable brackets, and the interpreter wouldn't have complained. It would complain only when I call next, because it will raise an exception. But I can always instantiate. If I try to instantiate here my iterable, it will tell me you're not supposed to do this. This is an abstract class. It has unimplemented abstract methods, so you're not supposed to do it. And this helps me out in debugging a lot, right? For the rest, it's the same. I mean, I use it in the same way, and it's name-based, it's safe, and one might argue it's not really that much Pythonic because you have a lot of boilerplate as well, and it's fine until you have one inheritance, but when you have like 5 or 6, it's going to be quite unwieldy to read, right? So somebody decided to, because of this, to implement also, to propose, accept, and then implement what is statically type-checked interfaces. This is new in 3.7, it's called protocols. And that's the next thing we discuss. So protocols have this nice thing that you can declare them, and you can implement them without actually telling the interpreter that you're implementing them. They are still be able to be statically type-checked. So let's go through this a bit, because this is, if here there was brackets, my iterable, that would be basically the same as ABC method classes. More or less, I mean, with some slight difference. But here, I am defining my interface here, leave alone the runtime checkable for now. I'm defining my interface here. Then I'm looking at what the implementation is just pass, or you can put ... here, or whatever you want, basically. You don't need an implementation. And in my implementation of the protocol, I don't have to declare it explicitly, so I can just implement it. But when I do def func object my iterable, and then I pass it an object that I actually instantiated through my class, the editor will be able to type check it and to tell you, yeah, this is fine. This is what you should do. It's not an error, right? And if I pass it something that is not implementing actually this protocol, it's going to complain. And this is quite helpful, particularly if you have like 4 or 5 different protocols that you're implementing in a single class. You don't have to explicitly tell the interpreter that you are in, or the editor in this case, that you are implementing all of them. You just implement the methods. And when you then check for those protocols in the function, you can actually verify at inspection time that those are fulfilled. So it's quite useful, right? Of course, if you are in most cases, you might want to actually explicitly state what protocol you're using, because it's not a bad idea. But there are some cases where this gets really unwieldy. And this basically gives you the spectrum. Let's go back 1 second. This gives you the spectrum of subtyping. Okay, so you have basically all of it. Usually, when we work with big applications, you might want to stick to nominal and static subtyping, because then people can read your code easily. But it's important to see the tools that are available, and it's important to know what exceptions you can have in your code, and particularly it's important to know the difference and when to use protocols, abstract base classes, and how to use them. Protocols is very lightweight. So whenever you're defining an interface, rather use protocols than abstract base classes. Yeah, abstract base classes, they are actually in documentation, they're like disincentivized to be used. They should be only used by the libraries and should only implement the abstract base classes that are already defined. But there are some cases where you actually want to do this because it makes sense. Otherwise, you just use simple inheritance. Okay. So now, the next question is, how do we use these tools? Well, when you're organizing your code, you have usually to take one big choice, right? So let's make a very, very concrete example. You have a program that is attached to some, for example, simulation or hardware, right? And you want to separate the logic of the program, like for example, some machine learning, from the act of communicating with the simulation or this hardware, right? And you might want to support different simulations or hardware. Right? So now the choice is there. Do you write a driver or an adapter that conforms to a certain interface and separate the two classes completely? Or do you write a base program, machine learning, for example, tool, and then you write a superclass, a subclass, sorry, that is specific for that simulation or hardware, right? And this is the basic choice that you have to take most of the time. So do I go for inheritance or do I go for composition? And there are advantages and disadvantages. But the basic, okay, first, I mean, what is inheritance? What is composition? Inheritance is basically when you use a direct subclassing, and it is you're overriding explicitly method of the superclass, right? This is inheritance. If you are subclassing but you're not overriding methods, you're just using, fake inheritance to just call methods from the superclass. To call method of the subclass from methods from the superclass. Well, this is basically composition in an inheritance setup, but it's not. You're not really using inheritance. To use inheritance means to override methods of the superclass and have tight coupling between the subclass and the superclass. The reason to do this are many. We'll see them. Usually, is to be avoided. If you can, stick to composition. Composition basically means that you have a class. You have some members, some fields, some attribute where you put your adapter or your driver or whatever you want to call it, and then you call one direction you call from the main class to your adapter, right? You don't know the details of your adapter from the main class. This is important. Again, both of these setups can be misused to actually create type coupling, or to, in case of inheritance, you can use inheritance where inheritance is not warranted at all. But the important part is that if you're using composition, the important part is that this member, this adapter, this whatever this is, doesn't know, the superclass doesn't know the details of this implementation. So if you're sticking, for example, an adapter in a field of a class, there are some things that the superclass, the main class should know about it, like for example, that it's managing some simulation. But it shouldn't know the details of the simulation. It shouldn't know the difference between different adapters. At the moment that you do that, then you're creating a tight coupling between the two. The moment that you change the adapter here, the driver, whatever that is, you have to change the main class as well. So this is where, if you're using composition, you have to be very careful. What's the role of these two objects, right? So this object, the main class, is the one that should know what's the goal of the member, what it should do, but it shouldn't know the details of the implementation. It should be sticking to an interface. While the subclass can know the details of the main object, because in the end it's not going to change, right? But if possible, it should also stick to the interface, because then again, if you change the main class, you have to change the subclass. So the looser the coupling, the better it is. Why is it to be preferred? Well, of course, right? For modularity. If you have composition, you don't have interdependencies between the two classes. You can change one respecting the interface, the other doesn't have to change. You change the other respecting the interface, the second doesn't have to change. While if you have inheritance and you go and change the superclass, you have to change usually the subclass. You go to change the subclass in ways that influence the superclass, you have to change the superclass. So why would one use inheritance at all? Can anybody have like an example where inheritance is actually inherently required? One example of this, where one place where you saw subclassing, you said, okay, without subclassing, I cannot do that. Or, it's very unwieldy to do it. Let's start from something that is said a lot in basic computer science classes. Subclassing means it's a relation of the type is a, right? A car is a vehicle. That was a typical example of subclassing. And in composition is a car has a wheel. Okay? So this is composition, part of the whole. But this is not all, because I could say typical example of where inheritance goes wrong. It's I don't like these examples because they're not really coding examples, but a circle is an ellipsis. It's the typical example where things go wrong. A circle is an ellipsis, yes, but it's a very specific one, and it cannot do everything that an ellipsis does. If I skew an ellipsis, if I elongate it, cannot do the same operation in a circle. So a circle, it's not an ellipsis is not substitutable in all aspects with a circle. So this is a is actually not really a good definition of what inheritance is. And inheritance is actually required where you need to expand an object, but at the same time respect all its API and be interchangeable. So one of the typical examples where inheritance is required is, for example, in UI. If you have a widget, you have a button, and now you want to create a toggle button, you don't want to recode everything that is a button, but you want to use every API that you already had in the button. You want to extend the rendering, for example, because you have a state toggle, not toggle, so you want to use the basic UI of the button, but then apply some filter on top of it, for example. And this gives you a very good case for inheritance, right? And the toggle button should fit right into the UI module that delegates all this stuff to widgets. So the same API should be respected. If you try to do this with composition, you'll end up in a mess. Why? Because you have to define a new interface for every extension that you do to a widget. You create now a new kind of widget, and then you have to create a new interface. So you have then a fauna of interfaces that nobody understands. Well, with inheritance, you have one interface that's the widget, and then you can extend it as much as you want. You just have to respect that interface. You can reuse all the code as well. If you do it with composition, you think about creating a toggle button from a button. How do I go and reuse the stuff from the main class? I don't have access to it. Somebody has to define an interface so that I can dock into the main widget. Otherwise, I have to re-implement everything from scratch. So this is a good case for inheritance, but there are not so many. So the main point of inheritance is really you have to respect an interface, you have to reuse the code, and you have to and you need actually the whole interface in your own class as well, right? This is the case for inheritance. Everything else is usually composition. Very important, because then you make your code decoupled, readable, and working properly. So how you go about composition? Well, you decide what's the main class, you decide what's the member, you stick an interface in between, and then you start coding towards that interface from both sides, right? So the class is going to, for example, if this is a networking adapter, the class is going to call you send packets, read packets, whatever that is, and then the details are going to be handled here. And you don't know how this is implemented. It could be file-based, it can be network-based, it can be whatever based. You don't care. Just there is an interface that clearly defines how they're going to work together, right? So let's recap. When to use inheritance? Inheritance is usually useful when you have overriding methods, and you need to because you want to reuse the code. When you have back and forth calls, like the subclass actually needs to call the superclass and needs to rely on that methods to be there, as well as the superclass needs to call the subclass and needs to rely on those methods being there, because there are some abstract methods that need to be implemented in the subclass. So when you have this double connection, you have overriding, and you need to substitute the abstract class or the superclass with the subclass in instances of your framework, then it's probably an inheritance problem. But usually, I mean, this is also a process, right? You start writing some monolithic piece of code, and then you start saying, okay, well, this part is actually part of network, and this part is actually part of simulation. I want to divide it and so on. You create a class, you create a subclass, and you start with this. And then you check, okay, is this really required? Do I really have to call back my superclass? Is this something that it's well designed? So you start refactoring your code, and at some point you might end up in a situation like this, where you have like your main class that has some specific methods that are the one that get called from the framework that you developed, and then you have some subclass that is only implementing certain specific stuff, like learn step. That's the learn step in your machine learning code. And it's just that get called one way. From the main class, gets called in this way. And then you have another method, which is, for example, read data, and then it gets called this way. You don't care about what's happening here, just implementing these methods. You don't care, you never call back, you just return things. Well, in that case, break the inheritance. Put this in a secondary class, define an interface, and be done with it. Because then you have decoupled completely this part of the code. And then you can test it in isolation, right? I mean, why we're doing this is, why we're doing this, because once you have decoupled it, you can test this stuff without this, and you can test this, the adapter without the main class, right? You can substitute a new adapter, you can substitute a new learning algorithm, for example, within the main class without having to work for it. So, useful inheritance example, what we said, right? You have widget subclasses, you have code reuse, you have automatic dispatching between subclass and the superclasses method. an access to base class properties if they are protected. I mean, we don't have such concept of protected in Python, but you get the idea. You have internal properties, you can just access them as self, and you go. And again, if you have to expose the full API of the superclass in your subclass or use the full API, it's probably again a case for inheritance. And then again, if you think about how would I implement this in composition, and you end up like having to generate like 3 or 4 more files, it's probably a good case to say, okay, I'm going to stick to inheritance because this is not a problem for composition. Advantage of compositions. Well, test both sides. This is a big one. First of all, you can test the delegate. I call it the delegate, the member of the main class. You can test the delegate in isolation, right? If you have, again, in a code implementing the learn step, and you have the main learning sequence in the main class, you can just create fake objects, NumPy array, whatever they are, pass it to the learn step and test that the learn step does what it's supposed to do. And you can do this in unit testing without instantiating all the machinery that you need for the main learning loop to go, right? So this is a big advantage because it makes, it gives you the possibility, you don't have always to do it, but it gives you the possibility to do test-driven design, test-driven development. On the other hand, you can test the main loop without actually doing any learning, for example, in this case, because you can fake the learning and just test that the main loop does what it's supposed to do. You can create a new adapter that doesn't do anything. It just takes an input, spits out some output that fits the definition, but it's not actually doing any learning. It's not using any GPU or CPU, so you can test it on your laptop. And you can test the main learning process very easily, right? That's the advantage of decoupling again, and it's used a lot. If you have resources like databases, networking, servers that you need to access in your code, and you need to make sure that your code that accesses these resources is working, one of the main advantages of decoupling is that you can fake those resources. You can fake the network, you can fake the servers, you can fake the databases, just by implementing some static fake interfaces that, you know, whenever you query something, they always give you the same result. But it's formatted correctly. So the main program wouldn't know. Example of a database. If I'm querying a big database and I need to do a selection of some users in this database, and I expect username, first name, last name. I can just create a static array of 5 users with first name, username, first name, last name, always return those 5, and then ignore that the database is not there and test my main program with it. Now I don't need to be connected to the server. In many cases, this is both a performance advantage as well as a possibility to code where you don't have continuous access to the main resources that you have in production, right? And of course, it's a clear information flow and a clear interface. Now, again, decoupling is important because it makes code readable. If you have a subclass that is tightly integrated with its superclass, it's very hard to debug one without the other. And it's very hard to follow the information across the 2 files, because usually these are in 2 files, right? So you need to think back and forth, what's happening here, what's happening there. Sometimes the superclass is not written by you, sometimes the subclass is not written by you. It's more rare, but again, it's very hard to debug. So, and it's easier for teamwork. If somebody is writing the main cycle, somebody is writing the infrastructure, and somebody else is writing for example, the learning step, you can write this stuff in isolation. You know what the interface is, you know what you're supposed to do, and there is no surprise, right? If you're writing with subclassing, you will have a lot more interdependencies. So again, when you change something, your colleague is going to have some problem. So before we finish, I wanted to show you some example of how protocols and abstract subclasses work. Let me go and presentation. All right, so why are those useful, right? So if I I mean, this is just the code that we saw before, nothing special with abstract meta and some implementation, a concrete class, and then I define a function that is taking my abstract meta class and calling the method on it, right? And the editor is happy with it, checks everything works. Then I have a second implementation and actually is checking the instance at runtime as well. So if I do this, you see, I don't have any problem with my editor. It's not showing me any error. It's showing this because it's supposed to be formatted in a different way. But this one is fine. Now, if I were to actually, for example, not implement this, so I will start receiving complaints. Fast Concrete must implement your abstract methods. So the advantage of using these tools is not only at runtime, it's when you start writing code. Most of modern editors have support for this. And they will start telling you something is wrong. And you know, in this case, it's a nominal type checking, so it will tell me at the definition itself. But for example, if I remove this and I start to, for example, pass something else here. Oh, sorry. So, well, in this case, I don't have value, but I can always do this. So now it's complaining that it expected my ABC and got an int instead, right? So when you implement these structures instead of using duck typing, the editor is going to be able to help you. So if you take at heart what's happening with the warnings, you will actually be able to avoid most of the mistakes before you start testing your code, which is very useful. And it's also going to protect from something like this. So now we're just going to run this. So let's comment this out. Well, this of course errors out because it's an int, but let me see if I get this right. Yeah. So can't instantiate abstract class my ABC with abstract method my method. So even at runtime, using abstract classes ABC meta instead of using just a class with raise method and implemented exception will help you because it will catch this line here as an error. Even if I don't use it, even if I don't call the method, it's going to already tell you cannot instantiate. It's an abstract class. So that's it. With the with protocols, you have basically the same advantages, but the interesting part is, okay, first of all, let's go through this. You define a protocol just by inheriting from protocol typing, okay? And if you want to extend the protocol, you can do this. You can extend an interface with another interface, right? What you need to do is just to inherit always from protocol, right? So a protocol is whenever you directly inherit it from protocol. If I don't inherit from protocol, my editor as well as my interpreter will understand this as a concrete class. So it expects then to be complete, right? But if I inherit from protocol, it will know this is also a protocol, which means I have to check, for example, that it's not instantiated. I have to check for when I pass it to something that is properly done and so on. The other thing is runtime checkable. So runtime checkable is a special decorator. What it means is, in standard-wise, if let's do a test, okay? So if I remove the runtime checkable, which is also an import from typing, and I try to do is instance object proto, you see it tells me only runtime checkable protocols can be used with instance and class checks, right? So if you define protocol and you try to implement this instance of, will error out. You cannot do it at this checking. This is optional because it doesn't work everywhere. That's the point. It works for most of the cases, but there are special cases, particularly with arrays and collections and so on, where this instance doesn't give you the right answer. And that's why it's not standard and default implemented. If you want to know more about it, you can look at the PEP 544. That's the Python proposal for the new feature, and it will explain it in detail why they kept it optional. But the important point is that if you want to actually do runtime checking, you just need to activate runtime checkable, and then this error goes away. And then you can just check is instance of proto, and you can check as it was a concrete class. Now, the interesting part is that in my concrete, I didn't actually specify that this concrete is actually extending proto or proto-ext, is implementing my math, is not implementing my second math. So if I go here and I tell it, run this on something that is proto, and then I check opt my math, is totally fine. When I pass it A, which is concrete 1, 2, 3, is not complaining. But when I check proto-ext, it's telling me, look at that, if actually would like to help out. Yeah, I expected proto extended and got concrete instead, right? So even if I don't declare which interface I'm following, the editor is able to pick it up from my code structure that I'm only implementing my first protocol and not the second, right? And this is again very helpful. It's very lightweight. It doesn't bring you any performance problem at runtime. At the same time, you have all the advantages of having a static type checking in your code. So whenever you write complex architectures, use protocols, implement them, make sure that you have a clear structure, because then you will end up with safe stuff. If I start doing something like this, sorry, I need to run from here. What do you expect? Can I instantiate it? Same as before, right? Protocol cannot be instantiated. So whenever I am actually trying to instantiate the protocol, I will receive this error. Same protection that I have with abstract base classes, I have also with protocols. Right? So that's it for today. It's a bit more theoretical than last time, I see. But it's important to look at this aspect, because the next few lectures I want to look into specific design patterns for different kind of problems that you might encounter in your programming. And I want to use these tools. So I want to make sure that you have a good understanding of what the protocol is, what an abstract-based class is, when I'm talking about inheritance and composition, why is it so, and what's the basic guidelines that we are going to follow into our implementation of design patterns. All right? Thank you.
Quick question.
Yeah.
In this class here,
yes,
the proto-ext inherited from these two subclasses.
Yes.
Which means these classes will have all the attributes and the methods from these two classes.
Right. Watch out. Protocol is typing protocol. So protocol is only defining this class and this class as protocols. It's not implementing anything, right? So this is like a mark. It's just marking this as an interface. Whenever I inherit directly from protocol, this is an interface. It's not a class. I cannot instantiate it. I cannot use it. There is no implementation. Okay, it's the same as for meta ABC. Right, it's actually not the same. because you can implement it, it's in a meta ABC, it's an abstract class. Think about this as a Java interface, which is probably more near to you, and the ABC as Java abstract class. It's really 99% the same, it's just slight differences. Any questions? All right, then I guess we'll stop it here. Thank you.